Hey guys, Mr. Burns here. We're talking lesson 2 here in Equilibrium. We're going to be talking about equilibrium expressions. So last time we talked a lot about what is equilibrium. It was a lot of theory. We're going to get into a little bit of the math of it today now. So equilibrium expressions, also known as mass... Oh, that's not what I want. Let's try one of these. Yeah. Also known as mass action expressions. I'll be calling them equilibrium expressions for, well, this entire unit. But if you do hear the term mass action expression, it means the same thing. I haven't heard that used very often. Maybe it's like a British thing or something, but just be aware of it. When a system is in equilibrium, we know that the forward and reverse rates are the same, right? Learned that last lesson. Which means there are both some reactants and some products in the system. So if we've got, I don't know, let's say table salt, and it is turning back and forth. It is dissolving into sodium and chlorine. Both would be aqueous. So if you were to look at your glass full of table salt, you would have some solid salt, probably sitting at the bottom of your cup, and you would have some sodium and chlorine ions. You'd have both, the reactants and the products floating around in there. Cool. Now here's the goal, though. We want to be able to tell how much reactant or how much product is in a system at equilibrium. So I say, hey, here's your glass of water. Here's 35 grams of sodium chloride. Once this reaches equilibrium, how much salt's sitting at the bottom of the cup? Now, you're going to need a little more information to actually solve that, but that's where we're going to go with an equilibrium expression. So to actually solve it, we set up what's called the equilibrium expression. So equilibrium expression, it's a mathematical expression that tells us at what concentrations the products and reactants have to be for a system to be in equilibrium. So it's basically just a ratio. Well, let's take a look at the equation here. It'll make more sense when we kind of look at an example. So here is our balanced chemical equation. I got some coefficient A for reactant A, some coefficient B for reactant B, some coefficient C for product C, some coefficient D for product D. See, did I say D? All right, we're good. So your equilibrium expression, you're going to have the concentration of C to the power C times the concentration of D to the power D divided by the concentration of A to the power A divided by, or times the concentration of B to the power B. So it is products over reactants. Very important. You always put products on top, reactants on the bottom. So it is a ratio of how, when you're at equilibrium, how much of your stuff has turned into products, how much of it has stayed as reactants. That's really all this constant is. So this constant tells you what is the ratio of products to reactants, and it takes into account your mole ratios, your coefficients, in these little exponents here. Things to note. Always products over reactants. I don't care if you have 14 products and one reactant, all the products go on top, all the reactants go on the bottom. The coefficients from your balanced equation become powers. So make sure you have balanced your equation before you start actually working through the math here. Because if you don't have a balanced equation, you won't have your coefficients properly, which means you won't have your powers proper. Kc, that constant, is called the equilibrium product constant. And it tells us how far the reaction has gone towards completion. Completion means everything is products. So if something went products, if something goes to completion, that means you've turned all of your reactant into product. Now, that happens sometimes, but with equilibrium, very unlikely. Kc tells you how close are you? How much, what's your ratio of products to reactants? Have you gone 90% of the way? Do you have 90% products, 10% reactants? That would show up in your equilibrium product constant. And similarly to the rate expressions we looked at in the last unit, that product constant is only valid at a specific temperature. Right? Remember how we were looking at like rate tables, and if you change pressure or you change temperature, you'd have to redo your experiment basically. You couldn't use K anymore. It's the same with this. If you change temperature, you would have to recalculate K. And again, we're talking about Y later in this unit here, but let's look at an example here first. H2, I'm going to rewrite these so they actually look proper. As a gas, plus I2 as a gas gives us 2 hydrogen iodide as a gas. All right, cool. Write the equilibrium expression. All right, so, well, our equilibrium product constant is going to be products, which in this case is HI. So what is the concentration of HI? To the power of its exponent. So it's concentration of HI squared divided by what are our reactants. I need the concentration of hydrogen gas, and I need the concentration of iodine gas, and both have a coefficient of 1. So you don't have to put the powers in if you don't want 1, and not having something written mean the same thing. But that's it. You're done. This is your equilibrium expression. That's what you could use to calculate how much one or the other you had, assuming you were given the missing pieces. Now, there's one thing to remember, or one thing to note. It's all based on concentrations, right? You can't change the concentration of a solid or a pure liquid. So if I give you a glass of water, like literally pure water, what's the concentration? How many moles of water are in there? Well, it's all water. And it's not dissolved in water, so you can't really say moles per liters of what. I mean, it's just water, right? So water doesn't have a concentration. It's just water. It just is. It is pure. So you can't use a pure liquid. Same with solid. If I say, hey, here's a salt shaker with some salt in it, what's the concentration of that salt? Well, again, I could figure out how many moles I have, but it's a solid. I can't figure out how many liters is in because it's not. It's got a fixed volume. Solids, that's one of their things, right? It's fixed shape, fixed volume. So you can't do concentrations of solids. So because you can't change the concentration of a pure solid or a pure liquid, you just don't include them in the equilibrium expression. So I've got solid salt breaks down into sodium plus ions and chloride ions. Now aqueous, now we're cooking with gas. I can work with an aqueous concentration. So if I want my equilibrium product constant, I've got two products, the concentration of Na plus, the concentration of chloride minus, and again, I don't have any coefficients, so I can skip those, divided by, well, nothing. I don't include sodium chloride. It's a solid. It doesn't have a concentration, so I can't use it. If you really, really, really want to include it, you can just put a 1 instead. Dividing by 1 doesn't change the answer, but it's much easier if you leave it off. You don't need it. If you have a solid or a pure liquid, you don't have to include them because they don't really have a concentration. All right, let's use it now. Let's see where we get an example. So same formula we just looked at there. Hydrogen gas plus iodine gas, I2, gives me 2 hydrogen iodide gases. All right. And now I'm going to get some information. I know the concentration of HI. I know the concentration of H2. I know the equilibrium product constant. I want to find out how much iodine is going to be left in my flask or beaker or whatever I'm doing this. Probably not a beaker, probably a stoppered flask because it's all gas. How much will be left at the end of my reaction here? So step 1, as soon as you see a double-sided arrow here, it's a real good hint that step 1 is going to be write your equilibrium product expression. So products to the power of the product's coefficient over reactants. Always products over reactants. You're going to be very sick of hearing me say products over reactants by the end of this unit because that's all we're doing, products over reactants. All right. Now we plug in what we know. I know Kc is 4.5. 4.5. Do I know HI? Hey, I do. It's 0.75. And I got to square it because I have a squared over there, right? I can plug in my iodine. I don't know my iodine. Do I know my H2? Yes, I do. 0.50. All right. So let's solve it. I pull my calculator out here so we actually see what I'm doing. Discipline tools, math, calculator. Okay. Biggest mistake a lot of people make in chemistry is actually calculator errors. So make sure you're using your calculator and getting used to it here. So fractions are evil. Let's get rid of the fraction. So to get rid of 0.5x, I times by 0.5x. So this 0.5x and that 0.5x cancel out, and I'm left with 2.25x equals 0.75 squared. You know what? I have a better idea. What's 0.75 squared? Is there no square button on this calculator? Oh, that's 75. 0.75 times 0.75. There, I'll square it the long way. Let's just replace that with 0.5625. All right. So how do I get x on its own? Divide both sides by 2.25. And x equals, where's my divide button? Divide by 2.25. What? That's not right. That answer makes no sense. 0.5625 divided by 2.25. Really? 1 over 4. There you go. I guess it does kind of make sense. Yeah, if I just estimate, it's dividing by 2. All right. I'm not crazy. I thought it should be smaller. 0.25. 0.25 what? What did I just find? Concentration. What are the units for concentration? Moles per liter, or molarity. I don't care which one you use. If you like moles per liter, stick with moles per liter. You like big old capital M, go for a molarity. Both work. So the concentration of iodine at equilibrium would be 0.25 molar. All right, so here's the same reaction. So we're going to use the same equilibrium expression. Hi squared over H2 times I2. All right, so same reaction. They're giving us all of the chemicals. HI is 0.95. Oh, these should all be concentrations. Is the system at equilibrium? How do you know? Okay, well, pro tip. If the system is at equilibrium, this is what the K value has to be. So Kc at equilibrium was 4.5. Well, if this is the same reaction, this Kc better be 4.5. Let's find out. I plug my Hi in, and of course square it. I plug my H2 in. I plug my I2 in. And let's find out what happens here. All right, calculator. Why can I never find my calculator quickly? I need to be able to like hotkey this or something so it just pops up. All right. 0.95. I wish I had a squared button. All right, so I've got 0.9025. Now, the reason I'm doing this in 2 steps is because a lot of times when people punch this into the calculator, this is what they type in. .95 squared divided by 0.3 times 0.3 because it's dividing by 0.3, right? That's not going to work because of order of operations. You'll get the wrong answer, not because your chemistry is wrong, but because your calculator didn't take into account order of operations. You got to put the brackets in there if you want it to work on your calculator. An easier way, if you want it to be really safe, do the top first, do the bottom second, and then divide those 2 numbers. Learn to use your memory buttons in your calculator. M+. I just saved it into my calculator. This answer that's written down. So now if I do 0.3 times 0.3 is 0.09. All right. So I want to do memory recall. Look at that. Brought back the number I saved. Divided by 0.09. Learn to use the memory buttons in your calculator. It'll save you a lot of time. 10.03 if I round that. Cool. So my K value is 10.03. Wait a second. My K value is supposed to be 4.5. So is this at equilibrium? No. Why? The Kc values are not the same. And if it's the same reaction, Kc needs to be the same. So this particular set of chemicals would continue to react and would continue to change until the Kc was 4.5. So you'd end up losing Hi and like losing from the numerator, gaining from the denominator until that fraction worked out to be exactly 4.5. That's why Kc is kind of so powerful, because it lets you solve that kind of stuff. One final note here, your rate expression that we did last unit and the equilibrium expressions here, they look very similar. So what's the actual difference here, other than having to use a rate determining step to find your rate expression? Well, in this case, rate constant is the rate of conversion of reactants into products, which means it's a speed, it's how fast it happens. Whereas equilibrium constant is the ratio of concentration of products to concentration of reactants. Kc has no actual unit. So Kc never has a unit. Now, there is a very long-winded and technical explanation for that we're not going to go into. If you get... we're not going to go into it. It's real complicated. Basically, if you really want to look into it, look into the difference between concentration and something called activity. And that'll tell you why we don't use units for Kc, because technically if you look at the math of it, you're like, oh, if I'm just dividing concentrations, sometimes they won't cancel out and I should have a unit, shouldn't I? Technically, we're not using concentrations when we say concentration of products, or we're using activities. For our situation, they're identical mathematically. There is no difference, but there's a small difference in the definition of them, which allows us to ignore units. So that's kind of the brief Coles Notes version of it. It gets real confusing really fast, so we're not going into it yet. But if you're interested, that's where you would look if you want to confuse yourself a little bit. But that's it for chemistry for today. So I will see you guys next time. Thanks for watching.